In this video, I want to talk about hyperbolic functions. At the moment, I cannot tell you why they're called hyperbolic functions. That I will be able to do at a later stage. Let's first look at this function. Y equals a half e to the x plus e to the minus x. What does it look like? Well, I've drawn the two graphs of e to the x and e to the minus x for you. What I would like you to do now is to pause the video and sketch what you think the graph of y equals a half e to the x plus e to the minus x looks like. So just pause the video. Okay, I hope, I expect, that you have ended up with a graph which is somewhere between these two graphs. You should have been going through there. Half of 1 plus 1 is 1. But exactly where is it? If I take a particular value of x, suppose I take x is here, at A, how can I describe geometrically where the point on this graph is? Somewhere between the red and blue graphs. Where? Well, let's just remind you of one thing. Let's suppose I take a half of m plus n. If m and n are 2 points on the number line, then a half of m plus n is bang in the middle. Same idea applies here. If I take x is a, then where it meets, or where we are on the blue graph, is e to the minus a, and where we are on the red graph is e to the a. Half of e to the minus a plus e to the a will be bang in the middle. So at this point where x is a, we have a point on the blue graph, a point on the red graph, and we are in the middle. If I take another point, a bit bigger than 1, there I am on the blue graph, there I am on the red graph, and in the middle. And we could do this lots and lots of times to find lots of midpoints. I've done this for you a few times, and if we now draw the graph of y equals a half e to the x plus e to the minus x, we get, and it did appear, we get exactly what we're expecting to get here. There is my half e to the x plus e to the minus x going nicely through all the midpoints. That was our first hyperbolic function. I now want to look at another one. This is very similar in its equation, half of e to the x minus e to the minus x. I can think of this as a half of e to the x plus minus e to the minus x. And by the same argument as before, this is now going to be the so-called midpoint graph between e to the x and minus e to the minus x. There's e to the x, there's minus e to the minus x, and here are a number of midpoints. And then if we draw the graph of y equals half e to the x minus e to the minus x, there it is. And this is the second of the two hyperbolic functions that we're looking at the moment. Now I want you to notice that if we differentiate the first function, half of e to the x plus e to the minus x, e to the x goes to e to the x, e to the minus x goes to e to the minus x, I get the other of the two functions I've been looking at. And if I take the second one and differentiate it, I get back to the first. Where have we seen something before that looks a little bit like that? Perhaps you might be thinking of this, that if I differentiate cos x, I get, well, there's a minus sine x, and if I differentiate sine x, I get cos x. So in some ways, differentiating these two functions, where they just swap round, is similar to differentiating sine and cos, where they just swap round, but there's a complication of an extra minus sign. This takes us on to the definition of what we mean by cosh x. Cosh x is the first of these two functions, and sin x is the second. Thinking of the connection between cos and sine, this is sensible. Cosh 0 is 1 and cos 0 is 1. Sin 0 is 0 and sine 0 is 0. So it makes sense to name them that way round. These are called hyperbolic functions. Again, I still cannot tell you why they are called hyperbolic. But carrying on with the analogy with trigonometry, we can think of hyperbolic tanh. Sin over cosh. If I differentiate sin by cosh and cancel the half, I get e to the x minus e to the minus x over e to the x plus e to the minus x. Some people like to multiply top and bottom of that by e to the x. And you get e to the 2x minus 1 over e to the 2x plus 1. Okay, my next question. What does the graph of y equals tanh x look like? Just pause the video for a moment and see if you can use these two graphs to help you draw the graph of y equals tanh x. So pause the video. Well, I hope you did pause the video. I hope you thought a little bit like this. Obviously, when x is 0, sin divided by cosh is 0 over 1 is 0. So tanh goes through that point there. What happens further up? Sin and cosh get closer and closer and closer. They get closer and closer and closer to e to the 2x over e to the 2x. But the top, the numerator, is always slightly smaller than the denominator. So this is always just a tiny bit less than 1. So as x gets bigger and bigger and bigger, tanh is going to approach y equals 1, but never quite reach it. An exactly similar argument will happen over here. If x gets bigger and bigger and bigger, negative, then this gets smaller and smaller. We're approaching minus 1, and the magnitude is always going to be slightly smaller than 1. So we're just above minus 1. So we're above minus 1, we go through 0, and we go out through 1. And there it is. You've got your two lines, y equals 1, y equals minus 1. The blue curve is contained between the two, goes through 0, and there is y equals tanh x. We can take this idea further. In ordinary trigonometry, we have sec. With our hyperbolic functions, we can now think of sec x. Sec x is 1 over cosh x. So what's the graph of sec x going to look like? Again, just pause the video for a moment and draw the graph for yourself. Y equals sec x. So pause the video. Okay, let's have a look and see. We are doing 1 divided by the dotted curve. 1 over 1 is 1. As cosh gets bigger, 1 over cosh gets smaller. And as cosh gets bigger and bigger and bigger, this gets smaller and smaller and smaller down to 0. And the same is going to happen on the other side. And there we have it, exactly as we were looking at. 1 over sin is cosh. So let's have a look at that. Same idea, we should be able to divide now a curve by looking at it. Cosh 1 over sin, here's sin. 1 over 0 is not very nice. 1 over a very small number is huge. 1 over a very large number is small. And of course, the same thing is going to happen, but negative down the other side. So there is coshec x. And the last one, of course, is coth, or 1 over tanch, or cosh over shine. This one I think is easiest to think of as a diagram as 1 over tanch. There is tanch. 1 over naught again isn't very nice. Small and positive, big and positive. This gets closer and closer to 1 from below. 1 over it will get closer and closer and closer to 1 from above. Symmetry tells us that that will happen on the other side. So those are your hyperbolic functions.